Okay, so we can start now. Sorry about the delay. I changed out my surge protector last night, and then I didn't make sure that the mic was still working, plugged into this new one, and it's not, and my speakers aren't working either, so should have done that. But everyone can hear me okay, right?
Yeah, the audio is a little more muffled, but we could hear you.
Okay, sorry about that. It'll be good though for today, right?
Yeah.
Okay. All right, so I don't think today should be too long because we're just doing a lecture. It should be pretty fast for that. And then after that, I'll talk about the first lab, kind of answer any questions you might have since I have to upload, another hour video for the lab report for the coding. So I know last time was pretty long. It was like a 2-hour lecture, and then I uploaded like another hour for that video. So does anyone have any questions that I can answer right now for the first lab?
Yeah, I have a question. It's only referring to when I was doing my coding, the graphs were, or was it the graphs? Something was, it was only going to 25 site, like it was really edgy, the graphs, and I was trying to figure out how to A, smooth it out, and B, make the time smaller. So when you're looking at the variables that it counts for, they're rounding to the nearest whole number. So instead of being 4.8, it's going to 5. So I'm just trying to figure out how to change that.
Okay, yeah. I'll help you with that once we finish today's lecture, but basically you'd have to make the step size smaller, so you can do that pretty easily in Matlab or in Simulink. And
Yeah.
then for the numbers, I think you just have to specify an integer.
Yeah, I know it's an easy fix. I just didn't know where to go with it. So it'd probably be like a 5-minute helping me out thing. But thanks, Pat.
Yeah. Anyone else? Okay, so first off, let me share my screen. There's something I need to update you for. So on the deliverables, turn this off. So the deliverables for the first lab are right here. I just modified something. So when we're comparing the analytic and our Simulink solution down here for position, velocity, and acceleration, you should compare the analytic solution to Simulink for cable 2. So if you already solved it analytically, I think you just have to change the stiffness. So that's it. So make sure that you're doing that comparison for cable 2, and then they should match up, pretty much exactly. Obviously not exactly, but your plots are going to be very, 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 very similar. All right. Okay, so the slides, they were updated last night, so you can go over that. I forgot, I can't show you guys the slides at the same time as I'm doing the lecture, but I think it's a good idea to have the slides up as well, so you can kind of follow along like that, but I'm going to write on my iPad. All right, I need to give my other account permission. Hold on. Sorry, I was delayed. One for my dog. She wants to go upstairs. So I take her upstairs, and then I had the issue with my mic. So how is everyone doing so far on the semester?
drowning.
Drowning?
It's stressful.
Yeah, it's really picking up.
Same.
Yeah, and then I've got a whole nother semester as well online next semester. So you're still waking up. Yeah. Okay, so let's get started. I need to pull up the slides on my computer. Okay. All right, so we're going to talk about experiment 2. This is the fundamental frequency of a beam. So most of our experiments in this class, we would actually just make an experiment basically inside of Simulink. Why did that disconnect? I think it's because my VPN turned on. Okay, so most of the experiments in our class, I think they would. Hold on, this is weird. This is like on my iPad. It's showing just my Note app. Sorry for all the issues. I don't know. Oh, okay. Sorry, I know why. I'm not on the same Wi-Fi network. Can you guys see my screen? It show like the screen mirroring thing.
Yeah,
Yeah, we see that.
Because on my iPad, I'm at a different spot, so it's like it's not connecting right. I swear I'm not this inept at technology. Alright, well, okay, I might disconnect really quick here. I'm gonna change my Wi-Fi. Okay, here we go. Finally, sorry. Let me just pull up the chat too. Yeah, my Wi-Fi name, we have like 3, I don't know, channels, because we have, 5G, another 5G, and then 2.4G. So we have Salar Morgulus, Salar Tahirus, and then Samuel Tarly. So Samuel Tarly, that's for the 2.4 gigahertz Wi-Fi, which is slower, so makes sense.
That's fat shaming, Patrick. That's bad.
Yeah, thank you. Okay, sorry. We've had a lot of delays so far, so yeah, I could do Horner too. Okay, so like I was saying, most of our labs, they would be inside of Simulink. We would just make some model in there, and then we would write a report on that. For this lab, we would typically actually do it in person. So we would go inside of the lab room, and we would have a beam in there, and then set up in the center of the beam would be a motor. This motor would have some external excitation on the beam, and then it would induce vibration on the beam. And we would induce this vibration, increase the RPM of the motor until we got resonance on the beam. So we would get resonance, then we would measure that, and we would add some more weight at specified intervals, and then we would have resonance for each of those increased weights. Obviously, we can't do that this semester because it's all online. So basically, I'll give you some data from the past lab, and you can look at that, and that's basically going to be your lab. So yeah. All right, so we're going to talk about the theory. It shouldn't be too bad again. It's pretty basic. So we'll get started now. Okay, so experiment 2, fundamental frequency of a beam. All right. Okay, so again, our goals. So I'm just going along with my slides right now. So the goals, we need to determine the natural frequency of our beam. We're going to determine the stiffness, the effective stiffness, and the effective mass of our beam. And we're going to compare that to theoretical calculations for that same stuff. And we're going to use a great name here, Dunkerley's formula, to determine the natural frequency of our lumped mass system that's attached to the beam. So our external weight, we're gonna look at that natural frequency as well. And then we're going to use Rayleigh's method to determine the natural frequency of a supported beam. So basically, we're going to have experimental calculations and theoretical calculations for the natural frequency, for the effective stiffness, the effective mass, and that's it. And then we're going to compare all of those. All right. So main goal, find the natural frequency of our beam. All right, so problem description. All objects, they have an inherent natural frequency, so that's the frequency that a system will oscillate at with no external force present. So if I have my phone, my body, desk, whatever, all of those are oscillating at some natural frequency. So if I have an external force, in this case, a motor for the experiment, if I can drive that motor at the same frequency as the natural frequency of that system, in this case, the beam, then we're going to have resonance. So those frequencies, they're going to, the amplitude is going to get larger and larger. And typically, obviously, bad stuff is going to happen. So I think this is pretty basic stuff, probably from vibrations, but we'll write it down. Okay. So I think so far, so good, pretty basic stuff. So if we want to avoid resonance, which we're not doing in this lab, but if you wanted to avoid resonance, you would find the natural frequency of your object, and then you just avoid that natural frequency for whatever external forcing frequency that you have on the system. Okay, and then for us, this will be going to use our external forcing frequency. So from our motor, that's going to be equal to our rotational speed. So the motor is going to be, it's going to have readings in RPM, and we're going to have to convert that to, I think we're doing hertz for this experiment. Okay, so the experiment I already talked about, we have our beam. We're going to add weight to the center of this beam, and then we're going to increase our forcing frequency on the beam till we get resonance. So we're going to have two methods to record this frequency of our beam. So let's write that down actually. Okay, so the first method is the frequency is going to be recorded inside of the lab view. Lab view, and that's going to be in hertz. And so for this, we would have basically a wire that's connected to our beam, and then that's connected to lab view. So we can directly read that forcing frequency on the beam. And then our second method is using a strobe gun. So from last semester, I assume all of you, or pretty much all of you, took 306B. So for the second lab, which we actually did in person, that was when we had a really long air duct, and you would have to use a strobe gun to read the RPM of the motor that we had. So if you remember that, we would be doing the same kind of thing here. There would be a little disc on our beam that would be rotating, and we would read the RPM of that rotation with this strobe gun. Okay, so those are the two methods that we have. And again, I'm going to give you basically a document that will have all of this data. So not as exciting, I guess, as a real experiment, but it is what it is. All right, let's talk about the theory now. Okay, so I hope you remember from vibrations how to calculate natural frequency. Okay, so that's going to be omega n equals the square root of k divided by m. So omega n, that's the natural frequency that we have. K is going to be the stiffness of our system. And then obviously m, that's the mass. Okay, so from this equation, we can write this in a different way. So we'll say that the natural frequency, we're going to rewrite this as the square root of gravity divided by y sub s. So y sub s is the static deflection of our spring. So our spring that's representing the stiffness of our system. Also, I uploaded the lab handout online, I think like earlier in the week, so pretty much everything we're going over now is on the lab handout. Okay, so y sub s, again, that's the static deflection of our spring. And this deflection is going to correspond to maximum deflection corresponding to an applied load. So let's draw a beam here. All right, here's our beam. Here's our load P. So if we have that load P, then obviously we're going to have some deflection in our beam. Let's get fancy here. We'll draw a pin and a roller. Maybe I shouldn't have done it. I think both ends actually in the experiment are fixed. So whatever, it doesn't really matter. So we're going to have some load in the center. And obviously this is going to deflect. So think back to 306A when you had your beam lab. You probably couldn't see the deflection because it was so small, but we measured that deflection with a gauge. And our maximum deflection was in the center where that load was applied. All right, so look how fancy this is. Okay, maybe not too fancy. Yeah, there we go. Can't really tell actually. It's a dashed line. The app I use got a nice update. Okay, so that's our deflection right there. So this is y sub s. So that's the maximum static deflection that we would have for some applied load P. Okay, and then we'll also say that the loading here is going to represent the total weight of the system. So while I drew an applied load P in this figure here, really this load is representing the entire weight of the system. Okay, so that sounds a little weird right now, but it'll make more sense in this slide. So I'm going to call this equation 2. And if we were going to use this equation for the lab, well, we'd have to measure that deflection. But there's really an issue with this equation because there's an assumption that the beam is massless. So when we are calculating our natural frequency, typically we do the square root of k divided by m, where m is the mass. So we rewrote that where we would look at the static deflection, but in this assumption, the beam is massless. So instead, we're going to use an equivalent system where we can have some equivalent stiffness Ke and some equivalent mass Me. So and then we have our stiffness and we have our mass, and then we can calculate the natural frequency in a more familiar kind of method that we knew from before. Okay, so assumes the beam is massless. So our approximation for that natural frequency is going to be pretty meh. Not going to be too good. So instead, we're going to use an equivalent system. Okay, so this equivalent system is just going to be a spring mass system. Okay, so we're going to have a fixed node right here. And we have our spring, and we have our mass. Okay, so our spring, case of E, that's the effective stiffness of our system. And then M sub E is the effective mass. Okay, so now that we have this system, again, it's more familiar to us, where we can calculate the natural frequency using some stiffness K, or K sub E, and some mass M sub E. So M sub E, that's going to be the mass of our beam, and K sub E will be the stiffness of our beam. Okay, so from this equivalent system, we're going to use Rayleigh's energy method. Okay, so Rayleigh's energy method for our equivalent system, this is going to define mathematically what our effective stiffness is and what the effective mass is based off of the geometry of our beam. So we have K sub E, our effective stiffness. That's going to be 48 times E sub I over L cubed. And then M sub E, that's going to be 0.4857 times M sub B. So let's define everything here. You probably know what everything stands for, but we'll be thorough. So E, that's going to be our modulus of elasticity, or Young's modulus, whatever you want to call it. Okay, so that's going to be a property of the material that we have for the beam. I'm guessing it says it on the handout, but right now I kind of forget, so I'm going to make a little note for myself to check that. All right, I just forget off the top of my head. Okay, I is going to be the second moment of inertia. Okay, so for us, we're going to have a rectangular beam. So we can just calculate that. So I is going to be the base times the height cubed divided by 12. Okay. And then we have L, that's going to be the length of the beam. So if these material properties aren't specified on the lab handout, which again I forget, it'll be with all the data that I provide you for the lab. So all the readings that we have in the lab, and then our measurements like the mass of the beam, the length of the beam, the height of the beam, and the width or the thickness of the beam. Okay, and then we have M sub B, that's the mass of the beam. All right, any questions so far? I think it's, hopefully it's straightforward so far. Okay. Okay, so like I said earlier, for our system, we're going to be adding on additional mass to the beam. So right now, we've only been talking about the mass of the beam itself, but for the lab, we're going to add on additional mass to the center of the beam, so we can look at a range of resonance frequencies. And we're going to call this additional mass capital M. Okay, so we can look at this, kind of model this out in a figure here. So we have one end that's fixed and the other end is fixed. So yeah, the figure I drew earlier with the pin and the roller, those should be fixed. Okay, so we're going to have now that's our effective mass, M sub E. And then below that, we're going to add our additional mass. So we would have like this little, I don't know, little support that would go off the beam. And we would add our additional mass there, just little weights. And then our line here is the effective stiffness for the beam. And technically, this is also massless. Okay, so this model that we have here, it's also modeling this stiffness. It's modeling after a massless beam, but that's okay because we also have an effective mass of the beam, which is here in the center. So we are taking the mass of the beam into account. Okay, now for this model here, we can find the natural frequency of the entire system. So that means the mass or the effective mass of the beam and our additional mass. Okay, so, this time I'm not writing out the square root, so that's why the left-hand side squared. So omega of ns, that's just at the natural frequency of our system with the added concentrated mass that we're going to have. And then Ke, that's our effective stiffness. M sub E, that's the effective mass. Capital M, that's the additional concentrated mass that's in the center of the beam. Okay. So this is one method that we have here. So let's actually box that. Okay, now we're gonna rewrite that equation. And we're gonna talk about Dunkerley's equation now. And again, what a name that is, Dunkerley. And this will let us solve for the effective stiffness and the effective mass experimentally. Okay, so for the equation that we just boxed, I'm going to call that equation 3. Okay, so we can rewrite equation 3. There's a lot of rewriting that we're doing in this lecture. So we're going to do 1 divided by 1 over, we're doing 1 divided by omega n sub s. Some of my slides, I don't have that squared, but I think this should be squared right there.
Yeah, I was gonna say that. I think they're supposed to be squared.
Okay, yeah. So let me make another note to fix that. Okay, so we have 1 divided by omega ns squared, and that'll be equal to m sub e divided by k sub e plus m divided by k sub e. So we kind of just took the reciprocal of what we had in equation 3. And we have individual terms now as well. And then from here, we're going to have omega 1 sub n squared. We're going to basically assign this variable here to k sub e divided by m sub e. So what we're doing here is we're kind of just taking that part right there and assigning some new variable to that. And then we're going to have omega of 2n squared. That will be equal to k sub e over capital M. So we have 2 expressions here, or 2 equations. So this first one right here, that's going to represent the natural frequency of the beam alone. Okay, so that's the natural frequency of the beam alone using our equivalent mass, which again, that's a function of the actual mass of the beam. And then omega 2n squared, that's going to represent the natural frequency of the added mass for the beam. Okay, so now we're going to rewrite equation 4 now. So this is equation 4. We're going to rewrite that. So we're going to have 1 over omega ns squared. And now we're just going to basically plug in the variables that we just created. So 1 over omega 1n squared, 1 over omega 2n squared. And this is Dunkerley's equation. Okay, so again, we're going to be using this to kind of calculate some experimental values in our system here. So if we look at equation 4, let's first call this equation 5, what we just wrote. So we can look at equation 5, or I think it's easier to look at equation 4 above. M sub v and K sub v, they're going to be a constant. Just remember, M sub v, that's our effective mass for our beam, and K sub v is the effective stiffness for the beam. And that's the beam alone. So that's without adding any external mass. Because if we add external mass, that's going to change the effective stiffness of the entire system. But M sub v and K sub v, they're just looking at the effective mass and the effective stiffness of the beam alone. So just the beam. So the only parameter that's going to be varied in equation 4 is capital M, or the added mass to the system. And that's going to be how we vary our natural frequency in the lab. Okay, so I'm saying the only variable that we can change here is the added mass. So if you change M, then you're going to change the natural frequency of the entire system with that added mass. Okay, so now we're going to use stuff from Dunkerley's equation here, and we're going to make a plot. And from that plot, we can then find the effective stiffness experimentally, and we can find the experimental effective mass as well. And also the experimental natural frequency of the beam alone. Okay, so let's draw our axes here. All right, gotta show that off. I think that's pretty awesome. All right. So on the horizontal, we're going to have our added mass, capital N. So for this, we're going to have either 4 or 5 data points, I forget, but we're going to start out with a 0 added mass, so 0, and I think we go to 4, 8, 12, and 16, something like that. Or maybe 4, I don't know if I said 4, 6, 12, but it's 4, 8, 12, 16, I think. Okay, so we have our added mass M on the horizontal, and then on the vertical, we're going to have 1 divided by omega ns squared. And so remember, omega ns squared is the natural frequency of our system with the added mass, capital M. So right there. Okay, so we're going to have these two variables here. So once we add our mass, then we're changing that natural frequency of the entire system. So now we're going to have some data points here, so we can make a plot. So our plot, it's going to be linear, because as we increase that mass, we're going to increase the natural frequency of our system. Okay, so here's our plot, and then from this plot, we can start to calculate some things from the plot itself. Okay, so the slope here is going to be equal to 1 divided by k sub v. So I'll do k sub v comma exp for experimental. So from our slope, once we make this plot, we can find our experimental effective stiffness from the beam. Okay, and then from our intercept right there, with the vertical axis, we can, that'll be equal to 1 divided by omega 1n squared, and that'll be the experimental natural frequency for the beam alone. Okay, so we can find that. And then we can find one more thing from this plot. Okay, so from our intercept with the horizontal axis now, that's going to be equal to our effective mass, or the experimental effective mass for the beam. All right, so you can find those 3 things from this plot. Okay, so we got one more slide here for the theory. So almost done. So now we have one more thing that we have to calculate for the lab, which will be the theoretical natural frequency of our beam. Okay, so up here in equation 3, this would be the experimental expression for the natural frequency of the beam. You'd have to find the experimental effective stiffness and the experimental effective mass, and then you could plug that in into this equation. Okay, so we have one more thing to go over, and that'll be the theoretical natural frequency of the beam. Okay, so for this, on the lab handout, it says like, if you can derive this, I'll give you extra credit. I didn't make the handout, so I don't know who did, but I'm not going to give you extra credit if you derive it, so. And I doubt anyone would want to, but if you do, good for you, but no extra credit. Okay, so the theoretical expression for the natural frequency of our beam is going to be equal to I squared E times I, the mass of our beam, and the length cubed, and all of that's going to be inside of a square root. So we already defined all of this before, but E, that's our elastic modulus, I is going to be the second moment of inertia, M sub B, that's going to be the mass of the beam, and then L is the length of the beam. All right, so do we have any questions? Okay, I'm going to assume that's a no. Okay, so the deliverables, they're on the handout as well. And so again, I don't make the lab handout, and they always have deliverables on the handout, but typically I like to upload a document for the deliverables myself. So I want to go off of the document that I give you, so I'll upload that sometime soon. And that'll basically include everything on the handout and anything more that I might add. I don't think I'm adding anything for this lab, but I'll make sure to upload a document that you can refer to so it's explicit on what I expect for the memo. So for this lab, we're going to need a least squares plot of 1 divided by omega NF squared versus our added mass, capital M. So we have 5 readings of the natural frequency. I'll show you, let me share my other screen. Okay, so this is the last slide on the slides. Okay, so we have that plot right there. Then we're going to compare the experimental versus theoretical natural frequency for the beam. And we're also going to compare the experimental and theoretical values for K sub E and M sub E. And then we'll determine is the strobe gun acquisition or is LabVIEW more accurate to find the natural frequency. So I think before, I'll need to go back in my lecture now and kind of think this through again just on my own. But yeah, we're going to be using the readings from the strobe gun and from LabVIEW. That'll give us the experimental natural frequency because we're reading that directly. So I think before I said you would calculate the experimental natural frequency from equation 3, but that wouldn't be correct because we're using that for our plot to find the experimental stiffness K sub B and the experimental effective mass M sub B. So Basically, to find the experimental natural frequency, we're using the strobe gun, and we're using LabVIEW. We can get that basically directly. Might need to do a little math, but not too bad. Okay, and then we're gonna look at sources of error. I know that's harder because you weren't actually doing the lab, but this is something that you'll have in your discussion part of the lab memo. So you'll be able to still have, a few ideas of what would maybe be inaccurate. I'm going to grade this part a little easier because, we're not actually doing the lab. But for this, probably a good place to start at is the strobe gun. How are we using the strobe gun? I remember from 06B, you have to be perpendicular to the reading that you're getting. So if you're at an angle, like a 40-degree angle or something, it's not going to be as accurate. So that would be something you could talk about. Maybe the readings, the measurement of our added concentrated mass, maybe that's a little inaccurate. So stuff like that you can kind of think of on your own. Again, I won't grade too strict on that part because I know you actually didn't do the lab in person. Okay, so any questions on this lab 2?
Yeah, I had a question about the notes that we were taking earlier. You
Okay.
said something about squaring something in the slides, but not in the notes.
Okay, so yeah, let's go back to that.
I was confused about that.
Yeah, so it's this slide right here. So slide 10. So in the notes that we just took now,
Yeah.
I had 1 divided by omega ns here. That was squared in the notes.
Okay, so the notes are correct, but the slides are wrong.
Yeah, I gotta update equation 4 in the slides here.
Okay, gotcha. Thank you.
I had just a quick question about the lab that we're going to write for the submarine one. The updated video with like the proper way to code it, that's just the week 4 submarine towing coding video, right?
I think that's what it's called. I can check though. Yeah, just this one.
Okay. That has like the solution where we ran into the problem with the max V-spot thing?
Yeah.
Okay.
So yeah, that video, it goes over almost everything that you have to do in the lab report. No, I say lab report, but I really mean lab memo. I didn't go over the analytic versus simulating solution for position, velocity, and acceleration. That'll be something you do on your own, but I'll kind of talk about that today as well. All right, do we have any questions on lab 2 or now on lab 1 for the coding or anything really? Okay, so I haven't seen any questions. I'm kind of surprised, to be honest, but if you don't have any questions, that's good. I already have it right here. Okay. So last night, I actually didn't solve it analytically. I will again, just to be sure. Actually, I guess I don't have to. So again, I didn't solve it analytically in the class before. I'm gonna have you solve that on your own. We did solve an example ODE, so it will be similar to that. But you need to solve it on your own by hand, and then you'll compare the plots to the Simulink solution. So looks like I only plotted acceleration here, but this plot here is the acceleration plot for the analytic solution and the Simulink solution. So in blue I have the Simulink solution, and in green I have the analytic solution. And this is for table 2. So remember that we're comparing the solution for table 2. If you want, I mean, you could do for table 1 as well, but that's going to be more work and you don't have to do that at all. So we have acceleration. I'm going to stop sharing my screen really quick because I have basically the answer for the analytic solution. Actually, you know what? We can share my screen because I want to see the work that you have to find the analytic solution. So that'll be something that you include in your report. You can put that in the appendix because I don't need to see all of your work in the body of the report for the analytic solution. So yeah, that'll be something you put in the appendix of the report. All right, so I'm going to uncomment some stuff here. Have fun, by the way, typing out the analytic solution in Matlab. Not gonna lie, it kind of sucks. You know, we solve for the position, and then we got to take the derivative of that for velocity, and then the derivative of that for acceleration. So here's the line for acceleration. Yeah, it's pretty long. And you also need to make sure that you do array multiplication. So that's when we have this dot right here. So we have a dot and then we have a star. You need to be sure you do that because we have what's called vectorized functions. So when we have exponentials and cosines and sines, and that's for some array. So like t out. So for our time, we have, from 0 to 25 seconds. That's an array itself. Sine of t out is an array. So if we're multiplying sine of t, and we're multiplying that with like cosine of t, we need to do array multiplication, which is why we have that dot before the multiplication sign. So you just want to be careful with that. So, you can, you can look at what I have here just to save you some headache. So I'm scrolling slowly and you can play it back later on. But I do want to see your work, so I want to make sure that you can solve this by hand. Okay, and then we have the analytic position up here as well. So if I plot all of this right now, we have the acceleration graph right here. So we see that they match up really, really well.
So the analytic is pretty much just putting in like the big, the homogeneous and particular solutions that we solve for into Matlab.
Yeah, so you'll solve for that, and then for your general solution, you have to, put those two together, and then you're going to plug that into Matlab.
All right.
Yeah, because our solution is, x of t equals x homogeneous plus x particular. Okay, so then this is velocity, or, yeah, that was velocity. I think I had my axes titles wrong. And then this is our position graph. Yeah. This is time, seconds. Okay, so do we have any questions on the coding for really anything for Lab 1?
Just how to make the
Oh yeah.
the thing that I was talking about earlier.
Okay, so I'll show that right now. So your step size, it's not for your graph. Well, yeah, okay, you're importing it from Simulink. So let's open up Simulink right now. I'm blind. Where is it here? Okay, so here's Simulink. So do you have Matlab opened right now too?
Yeah.
Okay, what's the size of T out? So
Uh,
if you're in Matlab, you go to your workspace.
Give me a second, my computer's running slow.
Okay.
Oh, really slow.
If the rest of you don't have any questions, then you're free to go, but this might be of interest too.
I think last time I saw it, it's opening up really slow, but last time I saw it was like 51 by 1,
Okay, yeah,
which is really small.
yeah. Yeah, so mine is 2,502 by 1.
Right. So all of my I watched the video you had yesterday, and all of my arrays are 51 by 1.
Okay. Okay, so I guess you can just look at my screen right now, and then you'll know what to do. So I'm in Simulink right now, and I'm going to go up to modeling on the top here. And then I'll click on model settings. And then inside of here, I'm going to go to the solver selection. So it's showing a variable step right now. Okay, actually, yeah, that's fine. So we can either have variable step or we can have fixed step. So in this case, I have it set to variable step. And then we just have to change the max step size to 0.01. And the variable step size basically, if we have a plot and we're getting to like a corner, so like think of a sine wave. Once we're getting to that corner, if we want that to be smooth, that needs a lot more data points there versus like on the more straight portion. So that's a way of variable step. All right, does that make sense?
Yeah, that looks.
Cool. All right, do we have any of those questions? Oh yeah, you also had a question about rounding, right?
Yeah, but that might be just because my step size was.
Okay.
So let me see
Yeah,
if
maybe.
I change it.
As for me, I'm not doing any rounding, and it's going to be more accurate if you don't round. So. All right. While he works on that, I'll ask one more time. Anyone else have a question?
I had a question for the EOM because I tried to do it the other day. I don't think I set it up right because my answer is different from yours.
Okay. From what you just saw in the plot?
Yeah. From what you had coded, your analytical is different
Oh.
from mine.
Okay. It might be, a little different. This is just when I solved it when I took the class, but the numbers should be very, very close. Did you do it for the second cable?
I initially did it for the first cable because I thought I saw somewhere where you had to do it. And then I saw that your handout said to do it for the second one only. So I did it for the second one again.
Okay. Okay. So you can stay on the call and then you can share your screen, I guess, or we could talk about it and then I'll go over it with you so you can make sure that's right.
Okay, I appreciate it.
Mm-hmm. All right, if there's no more questions, you guys are free to go, or you can stay on if you have an issue with that too.